Welcome to postgraduate research. While we all gather information in our daily lives, formal scientific research demands a much higher degree of rigorousness. It is a systematic, structured investigation, not passive reading. The formal research cycle begins the moment you isolate a specific, unanswered question in your field, your research problem. From there, you begin gathering facts. But collecting raw data, observations, and measurements is only the start. Without human methodology to extract meaning, these data points are scientifically worthless. We apply a strict chronological framework to derive that meaning. As this cycle shows, you start with the primary problem, break it into manageable subproblems, form intelligent hypotheses, systematically collect the data, and finally interpret the results. This cycle is continuous. When you analyze your findings, you inevitably uncover new variables and questions, which points the researcher directly back to a new problem. Research is not about finding final, absolute answers. It is about building rigorous frameworks to extract verifiable meaning from observation, constantly refining our understanding over time. Before you can lock in that initial problem, you must map the existing knowledge in your field. A literature review is an active, strategic mapping of theoretical frameworks, not a passive summary of past papers. This creates an operational paradox. You cannot execute an effective literature search without a formulated problem, yet you need the existing literature to figure out exactly what your problem should be. You navigate this by using early, broad searches to establish the theoretical roots of your topic. This identifies the agreements, the disagreements, and precisely where the gaps in current knowledge lie. Because the volume of global academic publications is overwhelming, you must implement strict search strategies to cut through the noise. We do this using Boolean logic. As the diagrams illustrate, linking keywords with "and" finds specific intersections, or combines related terms, and "not" excludes irrelevant categories. These modifiers force massive generic indexing databases to filter thousands of initial hits down to a highly targeted, manageable set of relevant abstracts. A systematic literature search prevents aimless wandering. It ensures that the new claims you eventually test are firmly anchored in established science. Once you identify the exact gap in the literature, you must transition from reviewing past work to actively framing the unknown. In quantitative studies, we do this by constructing a hypothesis. Fred Kerlinger defines this as an intelligent, conjectural statement regarding the relationship between two or more variables. This formal construction is distinct from the broader concept of a research question. Research questions generally guide qualitative inquiry. They are used to explore a phenomenon where the specific variables are not yet strictly defined. A hypothesis sets up strict mathematical or observational parameters. It directs quantitative data collection by dictating exactly what must be measured to prove or disprove the tentative guess. Choosing between a hypothesis and a research question dictates the entire methodology. It transforms a vague hunch into a concrete, testable claim. Let's apply this to a practical methodological scenario, researching the propagation vectors of a new malware variant within cybersecurity. The strict rule of academic sourcing applies immediately. We avoid standard web search engines for this investigation, relying instead on specialized bibliographic databases. To source peer-reviewed technical and computing literature on malware, you interrogate repositories like IEEE Explore and the ACM Digital Library. To verify the scientific influence of the journals publishing that data, we utilized broader, high-quality indexing databases like Scopus. Scopus tracks metrics like the Simago Journal Rank. This scale demonstrates how SJR calculates value. It looks past the raw number of citations and weighs the prestige of the journals where those citations originate. We also evaluate the researcher's individual impact using the H-index. An H-index of 10 means a researcher has produced 10 individual papers that have each been cited at least 10 times. Knowing exactly where to look and how to measure impact, we execute a systematic literature review, or SLR, on our malware topic. Before reading a single paper, you must establish strict inclusion and exclusion criteria. This determines exactly what qualifies as valid evidence for your study. Through systematic filtering, you methodologically reduce 1,000 returned database hits down to a manageable, specific set of 40 relevant papers. Executing an SLR using strict database metrics ensures your theoretical foundation is built exclusively on reproducible, peer-reviewed science. With the methodology set and the data gathered, we arrive at the final stage of the architecture: knowledge management and publication ethics. There is a definitive difference between an in-text citation, the mention of a source within the paper, and the full referencing list at the end that contains detailed publication information. Medical and technical fields often rely on the numeric method, also known as the Vancouver style, where citations are numbered in increasing order. The social sciences predominantly use the author date format. This table directly compares how the APA and Harvard styles display the author and year, contrasting them against the numeric sequencing of Vancouver and the page focus of MLA. To manage these formats, researchers deploying reference management tools like EndNote or Zotero. These platforms function as sophisticated personal research databases. These tools cross-reference your library with external monitors, like the Rutgers Retraction Database, automatically alerting you if a paper you intend to cite has been retracted or falsified. Citation systems serve as a critical defense for the scientific record, ensuring every claim remains anchored in verifiable, unretracted evidence. Violating the guidelines set by the Committee on Publication Ethics carries severe professional consequences, including retracted papers, canceled degrees, and academic blacklisting. Plagiarism takes several forms. Mosaic plagiarism involves patching together materials from different authors without citation. This is distinct from paraphrasing plagiarism, where you rewrite ideas in your own words but fail to acknowledge the original source. You can also plagiarize yourself. Self-plagiarism occurs when you replicate your own published data. Once an article is published, it becomes part of the permanent scientific record. Reusing it as new material violates publication ethics. This includes duplicate publication, submitting the same data twice, and augmented publication, where old data sets are mixed with new ones to prove a methodology established in an earlier publication. Another violation is segmented publication, or salami slicing, splitting a single dataset into multiple subgroups published separately. This artificially inflates a researcher's publication count while diluting the hypothesis. Detection triggers rejection of new submissions and revocation of published papers. Proper ethical attribution and avoiding data slicing are mandatory. They protect public trust and ensure credit is awarded strictly for genuine, original ideas. The scientific method is a complete chronological architecture. You map the gap through a literature review, frame the unknown with a hypothesis, filter your databases via an SLR, manage your citations, and publish ethically. Methodology is the engine that controls this entire endeavor, systematically extracting objective truth from raw observation. Your assignment is to apply this architecture. Define a specific problem in your field, identify 5 Boolean keywords, and run a preliminary search in Scopus or IEEE Explore. By mastering this systematic approach, you transform vague ideas into rigorously defensible, ethically sound contributions to human knowledge.